Hi, we are going to do a new chapter, wave motion. What is called a wave? Wave is nothing but a disturbance that travels from one point to another point. You cannot see a wave. You can see only the disturbance produced by the wave. When you go to a beach, I can see the waves, water waves I can see. The movement of water looks like a wave. Okay, so you can see only water. That's all. You cannot see a wave. The movement of water looks like a wave. Okay, so it is a disturbance which carried over from one point to another point, one particle to another particle. That is called a wave. Suppose you are putting in standstill water, you are dropping a stone. When you drop a stone, you are getting concentric ripples. You place a wooden piece over that. The wooden piece will oscillate up and down as well as it will move forward. The up and down oscillation of wooden piece is called particle vibration. And the movement of the wooden piece from one point to another point, we call it as wave motion. So this is one example of a wave. So under mechanical waves, we have two types: transverse wave and longitudinal wave. Transverse and longitudinal. What is called a transverse wave? The particle vibration and wave motion both are perpendicular to each other. Then you can call it as a transverse wave. Transverse wave propagate in terms of crest and trough. Crest is called the positive maximum, trough is called the negative maximum. So in terms of crest and trough, transverse wave propagates. Particle vibration and wave motion both are parallel to each other. That is called as longitudinal wave motion. Particle vibration and wave motion both are parallel. So here see, this is called a compression. This is called a rarefaction. Again, compression, rarefaction, compression, rarefaction. So waves as well as particle vibration both are in the same direction. That we call it as longitudinal wave motion. It travels in terms of compressions and rarefaction. Compression means region of increased pressure. Rarefaction means region of decreased pressure. One wave means it is combination of one compression and one rarefaction. One crest, one trough. Okay. The major difference between transverse wave and longitudinal wave. Of course, you know, transverse wave, particle vibration and wave motion both are perpendicular. Longitudinal wave motion and particle vibration are parallel. First difference. Second, it travels in terms of compression and crest and trough. Transverse wave travels in the form of crest and trough. Longitudinal wave travels in forms of compression and rarefaction. Transverse wave can pass through in solids and liquids. Longitudinal waves can pass in solids, liquids as well as gases, air or gas. I am talking something you are hearing in a classroom. Offline classroom, students are hearing. That is due to longitudinal wave motion. Because sound travels, you need air medium for the propagation. So transverse wave pass through in solids and liquids. Longitudinal wave pass through in solids, liquids and gases. Okay. Now, some definitions of wave motion. Oscillation chapter, we have seen the definitions based on simple harmonic motion. Here, amplitude, time period, frequency, wavelengths, wave number, maximum displacement of the vibrating particle, whether it is transverse wave in solids and liquids or longitudinal wave in solids, liquids and gases. The maximum vibration of that particular particle, we call it as amplitude. Time taken by the vibrating particle to complete one crest and one trough. One crest, one trough, the time taken. Or one compression and one rarefaction, the time taken. Before it completes one vibration, the wave crosses crest and trough. So that together, the time taken for that, we call it as time period. Frequency F is equal to 1 by time period. Vibrations, time taken by total number of vibrations. It is inverse. Frequency is inverse. Number of vibration per second. Sir, 1 second at all I cannot calculate. You calculate per minute. Whatever time you want to calculate, divide by the total time. Convert into seconds, divide by the total time. Wavelength or length of a wave. In the case of transverse wave motion, crest and trough, distance between two particles which are in the same state or same phase, we call it as lambda or wavelength. Particle 1 and 3 are in the same state. Particle 3 and 5 are in the same state. Sir, particle 1 and 5 are also same state. No, sir. Definitely they are in the same state, but two consecutive distance between two consecutive points which are in the same state of vibration only we call it as wavelength. Compression, rarefaction. Compression, rarefaction, compression, rarefaction. Distance between two compressions or distance between two rarefactions, we call it as lambda. Distance between two points which are in the same state or same phase, we call it as wavelength. Correct? Okay. Fine. Speed of transverse wave Only the final formula we are going to write. Whether it is speed of transverse wave or speed of longitudinal wave, final formula alone we are going to write. V is equal to root of T by M in solids. In a stretched string, wire is stretched. Other one side is fixed, other side you are suspending a load. We are going to see later. Sonometer. Stretched string. The velocity of transverse wave in that is root of T by M, where T is called tension in the string. How much mass you have suspended into G, that is called mg, that is called the weight or tension. M is called linear density. Linear density. Mass by length. Mass by length we call it as linear density. M. Transverse wave in solid, we have seen V is equal to root of T by M. Sometimes this is for a specific case, stretched string. Root of another formula also we can write, that is eta by rho. Eta we call it as modulus of elasticity. Modulus of elasticity. Modulus means magnitude. Elasticity means stress by strain. Modulus of elasticity. Stress by strain we call it as elasticity. In terms of length, in terms of area, in terms of volume, we have elasticity. All the three cases, stress by strain. We call it as modulus of elasticity. Linear stress, bulk stress, like that. Okay. Rho is called density of the solid. Rho is called the density. Velocity, if you want, you can compare. Left hand side unit is velocity meter per second. Right hand side eta by rho. Eta is called modulus of elasticity. Rho is called density. You substitute the unit of elasticity. You substitute the unit for density. Take a square root. You will get meter per second. Similarly, this case also. Then speed of longitudinal waves. Longitudinal waves. In liquid or gas, V is equal to root of K by rho. Again, K is called modulus of elasticity or bulk modulus, we can say. K is called bulk modulus or modulus of elasticity. Both are same. Bulk modulus means you are considering the entire volume. Rho is called the density of the substance. In solid rod, this is for liquid or gas. In solid rod, root of eta by rho. No, sir, eta already I have mentioned. Okay, y by rho. It is only a notation, man. Velocity of longitudinal wave is root of y by rho. Y is called Young's modulus, rho is called density. Same concept. Unit is root of y by rho. Unit is meter per second. Same concept. Correct? Only the final formula here we are writing. What are the various factors which affects the velocity of sound? Factors affecting velocity of sound. Effect of pressure. Effect of temperature. Effect of density. Effect of wind velocity. Before going to these factors, one important concept we have to read. Then based on that, we write the formula and proceed. Let it be as it is. Velocity of sound in gas. In gas or air. Two different formulas you are going to read here. One, Newton's formula. How Newton assumed the sound. Of course, when sound travels through a medium, pressure and volume of the system changes. Temperature remains constant. This is assumption made by Newton. Pressure and volume changes, temperature remains constant, means we have to take the equation PV is equal to constant. You have air medium, sound blows. When sound passes through the air medium, pressure of the system changes, simultaneously volume also changes. Then what is the velocity of sound? By Newton's formula. Here we are assuming temperature is a constant. Okay. Differentiate the above equation with respect to volume. Differentiation basics you know. With respect to V, we are differentiating. Both are variables. Keeping pressure constant, differentiate V with respect to V. 1. Keeping V constant, differentiate P with respect to V, dP by dV. Constant differentiation is 0. So I can write P is equal to minus V dP by dV. Minus V dP by dV. This is called the pressure. Okay, sir. Here, V is equal to root of Y by rho, root of K by rho, root of E. Whatever it is elasticity. Root of E by rho we have studied. E is called volume elasticity. What is the meaning? Stress by strain is a constant. Stress means pressure. Change in pressure divided by strain, bulk strain. Change in volume by original volume. Change in volume by original volume. Here is going to put a negative sign. Why negative sign? When pressure increases, volume decreases, provided temperature is a constant. That concept we are using. Take this V upwards, V dP by dV. This is called volume elasticity. But now we have proved P is equal to minus V dP by dV. Therefore, this formula changes. V is equal to root of E by rho changes as root of P by rho. This is pressure exerted by the gas or air. Rho is the density of gas or air. You substitute atmospheric pressure. You substitute density of air. Take the square root. You are getting the value V is equal to nearly 280 meter per second. But actual value is nearly 330 plus. Using Newton's formula, we are getting only 280 meter per second. Whereas Laplace correction. Laplace correction. Laplace argued that whenever pressure and volume of the system changes, no heat or temperature can enter into the system nor leave the system. That is called adiabatic process. What you have assumed by Newton is isothermal process. PV is equal to constant. When sound blows into a system, in terms of compression rarefaction only it proceeds. So you cannot talk about the temperature that is constant here. So he has taken the equation for adiabatic process. PV power gamma is equal to constant. Gamma is a constant. Ratio of specific heat capacity of gases. Gamma is Cp by Cv. You know very well by Mayer's relation, Cp by Cv is greater than 1. Cp minus Cv is equal to R is Mayer's relation. So Cp by Cv is greater than 1. Correctly speaking, you are getting around 1.42. It is a constant. That's all. Again, differentiate with respect to volume. Keeping P constant, differentiate V power gamma. V power gamma is nothing but x power n. Differentiate x power n. Nx power n minus 1. Like that. Gamma V power gamma minus 1. Plus keep V power gamma constant. Differentiate P with respect to V. dP by dV is equal to 0. Constant differentiation 0. It's a very important question. Newton-Laplace formula for velocity of sound in gas. Okay, now divide throughout V power gamma minus 1. Divide throughout by V power gamma minus 1. When you divide by V power gamma minus 1, this term V power gamma minus 1 cancel. And here you will get P gamma V power gamma minus 1 by V power gamma minus 1. V power gamma dP by dV whole divided by V power gamma minus 1 is equal to 0. Okay, these two cancels. V power gamma minus 1 I can write as V power gamma into V power minus 1. x power m plus n is x power m into x power n, like that. V power gamma minus 1 I can write as V power gamma into V power minus 1. V power gamma cancels. This V power minus 1 numerator will become V power 1. So I can write P gamma plus V dP by dV is equal to 0. P gamma is equal to minus V dP by dV, that is equal to minus V dP by dV. Already we know, what is the value? E, volume elasticity. So therefore, velocity root of E by rho becomes root of P gamma by rho. In Newton's formula, we come across V is root of P by rho, and we got the value 280 meter per second. Whereas using Laplace correction, we got the answer root of P gamma by rho. Extra one root gamma included here. Root of P by rho is 280. Root of gamma you substitute. Root of 1.42. Calculate. Find out. Multiply with 280. You are getting the answer. V is equal to nearly 332 meters per second. The exact coincidence with the experimental result. 332 meters per second. Of course, this is for 0 degrees Celsius, not at room temperature. Room temperature it changes. We will see. So 0 degrees Celsius, this is the formula. 332 meters per second. Velocity of sound in gas by Laplace correction. So we are going to use this formula for our further discussion.